In this session, I'm going to teach you the coding part related to the linear regression. Let's take an data set and let's solve a problem. So before starting, let's import the basic packages that are used over here. So let me import NumPy, and I'm also importing pandas library as well. So we know why you use NumPy and pandas. I have already covered in the previous lectures. So NumPy is used for array related operations, whereas pandas are used when we are working with data frames. So let me import visualization library as well. So we will import matplotlib, and also will you import the Seaborn library. So let's import warnings also. So to suppress the warnings, we use the command warnings.filter warnings. So let me import that as well. Import warnings. What filter warnings. Now figure out. Okay, so we have imported the basic packages that are needed for us to work with linear regression. So here, for performing linear regression, we might need stats model.api. So we will import that one as well. Import stats models.api as sm. Okay, so let's read the data set. So this is the data set that we are going to read, which is advertisement.csv. Okay, so here the first column is the index column. So let's mention that. So advertising is equal to pd.read csv advertising. So this is the data set. So let's mark this as index column to be 0. If we check the parameters that are present in the read CSV, we have index column as none. We are mentioning index column to be 0. This is our index column. So let me run this code again. Okay. So we have our data frame advertising over here. So now let's see the shape of the data frame. So the shape is 200 rows. We have 200 records and we have 4 columns as well. So let's see the data types of each of the column. That would dot info will give the data types, and also if there are any null values that are present in our data frame. So all the data types you could see here are in float format. So now let's see the 5-point summary of our data set as well as mean and standard deviation. For that, we'll use advertising.describe. So advertising.describe function will give you the 5-point summary, that is min, max, 25 percentile, 50 percentile, and 75 percentile, along with the mean and standard deviation. So the advertising data set that we have taken, we will see how advertisement of TV, radio, and newspaper have an effect on the sales dependent variable. Okay, these are the independent variables, and we will see which of the independent variables have huge effect on sales. Okay, so we have seen the describe function. So in describes, we have seen that the sales minimum is 1.6 and sales max is 27. And also we don't have null values over here. You can see no null values. So now let's plot a scatter plot. So let's plot a scatter plot where our dependent variable is sales and independent variables are TV, radio, and newspaper. In Seaborn, for visualization, we have pair plot. So in pair plot, we have parameters data. We will pass data is equal to advertising, and we will pass x vars. X variables are our TV, radio, and newspaper. TV, radio, and newspaper, and y variables, that is a dependent variable, is our sales. And let's see what are the other value variables, that parameters that are present. So kind, we will plot a scatter plot because we want to see how the data points are distributed for various TV, radio, newspaper independent variables, how sales is dependent on that. Okay. And also there is size attribute as well. So let's see what size going to give us. So there is size attribute of parameters. The parameter size, we have to put some value. Let me check what is that. The size, where is it? Size is none. Okay, let's not worry about size for now. So let's do the pair plot. So pair plot, we have to pass the data, which is advertising, comma, we have to pass x vars. X vars is equal to x variables are TV, a radio, and newspaper. Whereas our y variable is pass it like this, say it's okay. And we have kind is equal to scatter plot. We want scatter plot. Okay? By default, it's a scatter plot. Don't have to mention that. The kind variable. Okay. Okay. So see, actually, if you see the small size is too small, let's enlarge that one. So if you want to increase that size, you can mention the size class. Let me mention it as 3 and check what is the size. Okay, now still we need to improve this. So let me increase the size of the dimensions. Let me give size as 5. Okay, now the data is clearly distributed. So if you see the sales, how it is dependent on TV, radio, and newspaper, the sales is linearly dependent. You can see there is some relation between TV and sales. As the TV advertisements increase, the sales of the TV are improved and sales improved. And if you see the radio, there is some lot of scattering that has happened, and we don't have that much kind of a relationship. But yes, there is some kind of relation. If you see, can draw a linear line here, linear regression line, but the newspaper advertisements are like bit of scattered all around. Okay, we don't have no relation, it seems. So what we can do is that let's plot a heat map and check if there is any correlation. Okay. So as I told in the previous lectures, the correlation is we have to check for multicollinearity. Multicollinearity is nothing but if there is any dependency in the independent variables, So we'll check if TV, radio, and newspapers are having any correlation between them. So for that, let me plot heat map. In Seaborn library, we have heat map function and heat map. And what we'll do first, before plotting heat map, let's see correlation. Okay, advertising dot co. So if you see the correlation part, you can see that the sales is highly correlated, but it seems like there is no correlation between independent variables. First, let's check. So, okay, TV. Is there any correlation between TV and radio? So value is 0.05, which is neither close to -1 nor close to +1. Since it's a positive scale, so we'll have positive correlation. We have to check if it is directly correlated. So zero point zero 0.05 is negligible. Zero point zero 0.05 is negligible with newspaper, TV with newspaper, and zero point 0.7 is sales. So you can see that sales has a huge impact on TV advertisement. But it is obvious that this is a dependent variable, and dependent variable will obviously be dependent on the independent variables. So if you see the sales, let's see the sales. Sales have 0.78% of dependency, 78%, and 57% with respect to radio, and 22% with respect to the newspaper. So what we will do is that let's plot a heat map and you will understand it much lot better. As soon as dot heat map, we have to pass advertising dot correlation, and also you now need to map the color map as well. Let me take yellow, green, blue as the color. So you can go in Google and check the color map for heat map. There are various colors that are present. So by default, let me not use color map for now and just include a heat map. Okay. So in heat map, you can see that there are colors that are present. To see the values inside the boxes that are present, so you have to make a naught is equal to true. This will display the value inside the heat map. Okay, the value, that is the correlation values, it will display. Okay, so if you now see the correlation values, so you can see there are different colors. So 0 represents least correlated and 1 represents highly correlated. Okay, so let me change the color for now using color map function, color map parameter. So C map is equal to yellow, green, blue. Okay, this looks good, right? Okay. So you see, one means it is highly correlated, but it's obvious that TV is highly correlated with itself, and radio is highly correlated with itself. This is not the thing we have to worry. We have to see with the independent variable. So TV and radio, 0.005, it comes out to be here. So no correlation is present. TV and newspaper, no correlation, 0.057. TV and sales, this is an independent variable, so we are not going to worry. And now we'll check radio and newspaper. 0.35 comes out to be here, no, it's not correlated. Okay, so we don't have any worries. So now let's take you see here in the color map, when you have drawn the heat map, you can see sales is highly dependent on TV with a 78%. Okay, so let's see that was advertising of TV. Let's take X is equal to advertising of TV and Y is equal to advertising of sales. So now we are performing the linear regression algorithm. But before performing, we have to split the data into train and test. So let's check that. So before doing splitting the data, let's see the X data, that is X series and Y series. So X data, picture X. So this is the X data that is present. We have length of 200, okay, and Y data is this, okay, okay. So before doing that, so let's split the data into train and test. So let's split the data in the ratio 70:30. For splitting, we have to import train test split from sklearn dot model selection, import train test split. So now we'll take X train, comma Y X train, comma X test, comma Y train, comma Y test. Okay, let's do the splitting part. Train test split. So we are splitting the data into two parts, training data and testing data, so that we will train our algorithm with training data, and after that we will do the performance evaluation. So first we will pass the X data, X and Y, and we have to pass the train size. So let's give as 0.7. And we have to pass test size, but which by default it will consider 30%. Let's pass it even though it's not required. So it's your wish to pass test size or train size, but you have to just pass either one of the parameter. So I'm going to pass both test and train over here. So pass random state as well, so that when you run the code again, whatever data that is splitted, it will split in the same way. Okay. I mean, the same data are splitted when you put the random state is equal to some value and run the code with the same value. Okay. Okay. So we have now invalid syntax. Let me see what's the problem over here. X train, right? X train, comma X test. Invalid syntax X comma Y. Okay. X is this, Y is this. Okay. This is okay. So now let's take a look at the extend data. So we have 140 values. So and white train data as well. We will check. So before that, let's check X test data as well. Test dot head. Okay, this is the testing data. We have just considered only the head part, that is top five values. So now let's apply the stats model.api. So stats model.api is a statistics function, statistics library, which is used to perform the linear regression. We will perform the linear regression algorithm using stats model.api. We will use the algorithm ordinary least square. So stats model is a Python model that provides classes and functions for the estimation of many different statistical models, as well as conducting statistical tests, and also do statistical data exploration as well. So this is about stats model.api. Let's import that. Import. So we have already imported, it seems, stat model.api. Let me copy this and let me paste it over here. So the theoretical part, I forgot to explain more about heat map. So heat map is a matrix kind of two-dimensional figure which gives a visualization of numerical data in form of cells. Each cell of the heat map is colored and shades of the color represents some kind of relationship of the value with the data frame. Okay. Usually we use heat map to find correlation. And about pair plot, if you want to know, so pair plot is to plot multiple pairwise bivariate. Okay. This is not univariate. Univariate is like single variable, right? So here we are taking bivariate, it is multiple variables. So it's a pairwise bivariate distribution in a data set. You can use the pair plot function for this, and it is used to analyze the data distribution. So now let's come to the import stats model as a API. So this is the stats model, okay, statistics model. So now what we will do is that we will add a constant to get an intercept, okay? So here is our extend data, right? So for this extend data, we will pass an intercept that is a default value, okay? That is a default value that will be passed by the machine. Okay, you don't have to worry, it will actually add constant internally. So for that we have to pass xtrain underscore sm is equal to sm dot add constant. Okay, so we have sm dot add constant. So let's see what does it do, the function sm dot add constant. So sm dot add constant, you have to pass the data, and data will be like array column order design matrix. So what happens is that the original values with the constant as the first or last column, return value type depends on the input. Okay, so if you want to know what happens with this bad constant, you just add us a constant. Okay, the value constant add constant will make sure that it will have an intercept. Okay, so your data that you are going to train would have an intercept. For that we have to add a constant, like let me comment it out here. So it adding a constant that is to get an intercept. So you know the equation of line, that is regression line, will be in the form y is equal to mx plus c, right? So we know that in m into x, right? So m is the slope and x is the independent variable, and c is the constant. Okay, so we have to pass that constant value over here. Okay, and we do you don't need to worry about that constant part. It will by default take some default value over here. We have to pass this default value because it's not add constant on this. Okay, we have to pass here x train. Okay, we have passed x train over here. So now we have to fit a regression model using ordinary least square. Fitting a regression model using ordinary least square. We passed of SM. So we have passed intercept. Now we have to train our model. So for training our model, let's take variable s. Okay, let me take the stats model sm dot. So now we have ordinary least square OLS OLS. So let's see the ordinary least square function. What does it do? So ordinary least square is an algorithm. Okay. So let's see what does the algorithm do. Okay. So you have to pass your x train and y train over here. So y train we have to pass first over here. So first attribute will be y train, and the second attribute will be x train Sn. So this algorithm is going to train our model. For that to happen, we have to dot fit. So this is going to train our model. So we have passed the constant, but by default, it will take a default constant. So according to the ordinary least square, it will actually do the gradient descent kind of thing, and it will choose the intercept as well as constant. Okay, this whatever constant you have passed is a default value, and so we have to pass this default constant over here because otherwise this algorithm won't work. Okay, so based on whatever value you have passed, it will try to optimize that value. So whatever constant you have passed, it will try to optimize that value in a way that will get a slope as well as intercept. Okay, we'll get slope as well as intercept. So x drain. So to see that, let's see lr.params. lr.params. Okay, lr.params. So this lr.parameters will give you the constant and as well as the slope. So the slope is 0.05 and the constant is 6.7. So if you do see the pair plot, 6.7 comes out to be here and it is like this. So the regression line is passing in this way. So let's plot that. Okay. For the given slope and constant, let's plot the regression line. Okay. Before doing that, let's see the summary of LR. What does it do? If you see the summary of linear regression line that we have just created, so the linear regression line, so it has an R square value. The model has an R square value of 0.64, that is R squared is 64.1%, whereas adjusted R square is 63.9%, and the model that we have used is ordinary least square. So this is how we train our model and we get the best fit line. Okay, so we get a best fit line. So I'm going to repeat this once again. First, we'll import the stats model. So for statistical operation, so in the stats model, we have uh, ordinary least square function, so algorithm. So before using the ordinary least square algorithm, we will have to add constant to our extrain data so we can able to optimize the constant value. Okay, if you don't pass, we won't be able to get the constant value. By default, you have to pass the constant value so that we will actually tune the constant value in such a way that we get for whatever x train and y train we have, we will get the slope and intercept. And intercept will be tuned here, and we will get slope when we have passed the data for x train and y train or ordinary square algorithm, and then we have trained the model using dot fit. So dot fit we have used to train our model. Then we can check the constant as well as the slope using dot params function. Dot params function give alert that the linear regression line that we have created. Dot params give the parameters constant and the slope. And LR dot summary gives the more advanced concepts like it will give R square, adjusted R square. It gives the model which we have used, and also it gives the coefficient, that is coefficient of x, that is 0.05, which is the slope, and also the coefficient, the other coefficient, which is the constant, that is 6.74. So now let's draw the regression line for that data set. Okay, let's draw the regression line over here. So for drawing the regression line, we have to take plt.scatter, plt.scatter of, let's see the attributes. X we have to pass. X is x train, x train, comma y is y train. So this is how our data is distributed. So now let's draw the linear regression line. Plt dot plot of, so how we want to plot this. So So we have seen the equation y is equal to mx plus c. So here m is our 0.05. So 0.0502 m into x is our x10 plus c. C is our constant, which is 6.7453. And what is the color of the regression line you want? So color of the regression line we want is red. So this is the y value that we have passed over here. Y, x is x10. So y is mx plus c, m into x10 plus c. So let's plot the regression line. So there is some problem. So color, okay, color we had to pass. Color we will pass it as red. Okay. So what's the problem? This is 0.67. Sorry for the mistake. 0.67 it is. 0.67. What's the mistake? Let me check it once again. 0.0502 into x10 plus zero point 0.6. So this is 6.7. What is the 6.7 coefficient, right? Okay, so there is some mistake still. X train, comma y train, plt dot plot. Okay, let me check it once again. So this slope is 0.05. Sorry for that mistake. So 0.05 we have to give. So we this is in the form y is equal to mx plus c. So x10 is our extended x10. So let me plt dot x label of. So this is our x10. Plt dot y label. This is our y. Okay, so we have our x and y, and we have plot the regression line over here. So this will cut over here at 6.7453. Okay, so you can see how it will cover almost all the data points across the regression line. Okay, so you can see most of the data points are around this, and you see there is some kind of a distribution where we have plotted the regression line successfully. So now we'll do the error analysis. Okay. So now we will do error analysis. So now we will do the white train prediction. Okay. White train prediction. So white train prediction can be done by passing our model, which is LR model dot, then what? LR dot predict, LR dot predict of X train. Okay. So now the resultant, that is the residual or the error, is going to be y train, which is our actual, minus y train predicted. Okay. So this is what is a residual or error. Okay. So we have done the prediction. So this is, sorry, this is xtrain dot underscore sm. Is it? Xtrain underscore sm. Let me check that. Xtrain underscore sm. Yeah, that's extra because we have passed the intercept, right? I mean, we have passed the intercept by adding a constant. Okay, so we have to pass that value over here, and our linear regression line will do the prediction accordingly. So, and it will, now we can see the error. So error is nothing but the predicted, that is actual minus predicted, that is the error. So now what we will do is that white train predictions. Okay, so there is some mistake over here. White train y train control z y train minus y train predicted. Okay. This is y train minus y train predicted. Okay, so we have got the value, the residual. So now we will plot the histogram, plotting the histogram gram of errors. Okay, so for plotting the histogram, we will to plt.histplot. So we'll do a plot dist plot. Okay, distribution plot. plt.distplot where we will pass residual and how many pins we want. We want 20, 15 pins. Matplotlib has no attribute called distplot. Okay, but we have distplot in Cborn, right? So we have plotted the distribution plot using Seaborn library, and you can see most of the errors, I mean, between -5 and 5. So error, that is predicted minus actual error, almost all of the values lie between -5 and +5. Okay. So there is not much deviation. You can see here as well. So if you see this point and let's consider the value over here, and it comes out to be around 13 or 13. Okay, and this value comes out to be 20. So 20 minus 13 is 7. Okay, so 7 is error means over here, it lies over here. But from this data distribution, you can see almost all of the errors lies between -5 and +5, and all the errors lies between -9 and +8 something. Okay, and we can see more of the error are like zero errors. Okay, the actual and predicted coincide almost, like this here almost. Okay, here these points are coexisting. Okay, so most of the points are whatever is predicted it, and whatever is actual are almost same. Okay, so it comes out from here to here. Okay, from this region to this region between -3 and +3, most of the error lies. So we have actually plotted the distribution of errors. So now what we will do, we'll do this. We will apply the same concept for trace testing as well. Okay. So we have performed for 10. We will now perform for test data. So x test dot underscore x test sm is equal to what we'll do. So now we have to predict, right? So we have to apply the intercept, that is adding a constant. We have to perform the same operation of adding a constant to get an intercept. So x test sm is equal to xm dot add constant of x test. Okay. So we have added an intercept. Now we will do the prediction. Predicting on test data. So let's see what is the value it comes. So y test prediction is equal to LR, that is our model, LR dot predict of X test SM. What is the problem? Ordinary least square has no attribute predict. So that it is not predict, it is predict. So now we will see the residual error, that is y test minus y test. So we have got the residual. So now we'll plot the same distribution plot for this as well. So, but let me give some more parameters for here. So let me pass the title as error terms. X label as is the X label residual error, right? Residual error. What's the Y label? Y label is nothing but Y label is frequency. Okay, I got this. So similarly, we'll plot this for the testing data as well. So let's see the value. Okay, first let's run this and run this. So this is how the error for test data that we have got. So 30% data that we have taken as test data. This is how the error is distributed. And if you want to draw the regression line for the test data as well, so let's plot that as well. Plt.scatter of x test. So plotter we have to pass for scatter plot we have to pass x test and y test. So we have passed the same right x test, y test. So this is how the data is distributed, the test data set. So now we will do plt.plot of let's pass x test, comma y test is nothing but y test sm, right? No, y test is nothing but y mx plus c. That is m is 0.05 into x test plus 6.74 something 6.743 to something 7453. So we have passed x, y. Let's pass the color to be green, maybe. Okay. So you can see this is the regression line for the test data as well. The regression line will be same for train data and test data where the slope and intercept is already defined. I simply showed you that. Mm. So now we have already seen the distribution, the error, how the error is distributed. So most of the error lies between the range with the residual between -9 and +7 difference. But if you see the percent, this gives the percent, the whole, this from here till here, it gives around percent to be 25%, 0.2, 2.5, 7.5. Almost all the data is distributed between this. I mean, with errors this. So, but the data is distributed like this, and we have the regression line with a slope of 0.05 and intercept of 6.745. So here also this is test data error terms. Okay. So this is test data error terms. Here also it will give residual and frequency. Okay. So now let's calculate the R square. So for calculating R square, what we can do is that we can just pass uh, the regression model, right? This is the regression model that we have plotted. You have to just pass LR dot R squared to get the R squared value, or you can just pass LR dot adjacent R squared to get the adjacent R squared value. Okay. Let me pass LR dot R squared. So LR dot R squared is 64.1% for this. So you can see the value of R squared is 64.1%, and the value of adjacent R squared is 63.85%. Okay. So we know that R square, adjacent R square will always be less than or equal to R square. Now what we have to do is that this R square and adjacent R square, what it will give is that what are the independent variables that have been contributing hugely to the sales. Okay, that is the dependent variable. So the TV, how it is contributing to the sales. So we have seen that R squared has increased. That is R adjacent square has increased. I mean, it is 63.8%. Okay. So now what to do? You can consider two. That is, instead of considering only advertising over here, that is advertising of TV, you can pass advertising of TV is considered here. You can pass here TV, comma, newspaper, and newspaper, comma, television, and TV, comma, newspaper and television, and TV, comma, newspaper, TV, comma, radio. So you can do those kind of operation and see which are the independent variables which is giving the highest adjacent R square. Okay. So the highest value of R square adjacent means so those independent variables having huge impact on our dependent variable. And wherever there is a decrease in R square adjacent, with increase in independent variable, then that particular variable doesn't has any kind of positive impact in your output data set. Okay. So if there is no positive impact on your output data set, then it will decrease your R square adjacent. Okay. So first check with one variable, then increase it by another one, and then increase it by another one, and check if the adjacent R squared is increasing or decreasing. As per adjacent is decreasing, then you have to drop that independent variable. And if R square adjacent is increasing, then you have to consider that independent variable. Okay. Hope you understood that concept. And now let's draw the regression line by using linear regression model. Okay. Before moving to applying the linear regression model to our data set, what we can do is that let's see how R squared and adjusted R squared behaves for various independent variables. Okay, so we have passed X as advertising of TV, we have passed TV, and we have seen how TV is having influence over the sales prediction. Okay, the sales data. Okay, so now from the heat map you can see after TV the more influence that the sales has is on radio. Okay, so if you see here sales for TV was 0.78, we took that. Now let's apply radio and see what is the adjusted R squared that comes. Okay, so now we will pass radio over here. So now let's run all the code. What's the problem here? Advertising of TV, comma, radio, right? Uh, that's the problem. Let me check. So we have passed it in the form of list. And now let's run the code. Xstate. Okay, we have got test.head as intercept parameters. So what are the parameters for TV? We have a slope of 0.04, and we have for radio, we have a slope of 0.18, and constant is 2.95. A lot of summary. So we have adjusted R square here as 89.8%, and R squared value is 90%. Okay. So now let's see the plot as well. Okay. Uh, okay, wait, let's not do this. Mm, let's go back. Let's pass TV again. TV only. We wanted only adjusted R square, right? So we wanted to check which are the independent variable that has a huge effect on the sales. So we have got which independent variable. So now we had passed here uh, radio as well. So we wanted to check how the sales data varies for that. So we had got constant 2.9 slope for TV and radio. And now let's run this and check the R square and adjusted R square. So with one variable, that is TV, we got our adjusted R square as 63.9%. Let's run it again for TV and radio this time. So for two variables, we got adjusted R square 89.8%. So it's a good value, right? So now instead of taking TV, radio, now let me take newspaper as well, okay? Newspaper. So now with two variables, we got a good adjusted R squared value. Now we will check for three variables, what is the adjusted R squared. So we have got three variables, TV, radio, and newspaper. And we have our parameters where so for newspaper is negative. So let's see. So for TV and radio, we have adjusted R square of 89.8%. If this value decreases now with inclusion of newspaper, then we might have to drop newspaper and we have to consider only TV and radio. So let's check that. So here 89.8 for TV and radio. Now let me run. Okay, so you could see that after I run this code, there was no influence of newspaper. I mean, there is a negative impact or there is no improvement from the previous value. So we can, from this data, we can say that the dependent variable sales has a positive impact if you use TV and radio, whereas the independent variable newspaper has negative impact or no impact on the sales data. From the scatter plot also we could see, so there is no relation, right? I mean, from sales and newspaper, there is no relationship at all, okay? There is no kind of relationship or regression line that will actually predict the values for our newspaper advertisements. So newspaper advertisements has no valid uh, dependency on the sales data. Okay, and here also from the heat map also you could have seen there is no correlation. I mean, these correlated the newspaper data with the sales. So what we can do is we say is that TV and radio are highly I mean TV and radio has a high values of adjacent R square and R square, and we can say that TV and radio are the independent variables that should be considered for our model. Okay. So what we can do now is that let me just take TV over here now. So we have already seen, right? So let me run all the code once again. Okay. So we have performed the ordinary least square algorithm on our data set. Now it's time to use linear regression model. So ordinary least square was a stats model, whereas for applying linear regression model, we have sklearn dot model. So from sklearn dot model import linear regression. Okay, LM linear regression LM is equal to linear regression. Okay. So we have imported our linear regression. So before, okay, what is the problem of sklearn dot model from sklearn dot linear model? Sorry, this is linear model, right? So, once again, we will take our data set. We will split our data set into train and test. So X train, LM. So let me take the same data set over here, the splitting. So from sklearn dot model selection, import test split. So let's draw a regression line for using linear regression model. Okay. Xtrain, let me call this as Xtrain LM. And this is X-test LM. This is Y-test LM. LM means linear model. Okay. So, okay, we have our X and Y, and train size is 7, and test size is 0.3. Okay. Okay, so now, so this has changed. Okay. So now we will apply linear regression algorithm to build our model. So lm dot fit lm dot fit of X train linear model, comma Y train linear model. What happened? Okay, let me check what happened once again. LM is our linear regression. Okay, X train LM. This thing Y train LM is our Y train LM is our this thing. Train test split of X train coin train. Okay, what's the error? Linear model, right? So, here it says that expected 2D array got 1D array instead. So it's saying that reshape your data either using array.reshape if your data has a single feature. Okay, so we had our data has a single feature, right? I mean, extrain whatever we have taken. So we have to do the what we have to convert our 1D array into 2D array. Okay, so for that, let's write a code about. So extrain LM. Once again, we have to do that. Extrain LM. We will take extrain LM is extrain extrain LM linear model dot reshape of what it's saying -1 with one column. Okay, -1 comma 1. And white train also will do that. Let me see extrain LM now. Extrain LM. Okay, what's the problem here? We have seen that extrain dot reshape series has no attribute reshape. Extend lm dot values. Okay, dot values dot reshape. Okay. Okay, so now we have converted our 1D array into 2D array. So what we took is that, so first we took extend dot values, extend dot lm dot values as no attribute for values, extend lm dot reshape. Let's complete reshape. We applied reshape function. That's ls values. Lm dot values NumPy.nd has no attribute values. Okay. Dot reshape of -1, comma 1. Okay, so we have taken the values from this extend ALM linear model and we have converted into two-dimensional with only one column. So reshape function, what does it do? If you want to check. So okay, we will now be worried about the white train as well. So white train LM is equal to white train LM linear model dot values dot reshape. Okay, so we are converting our 1D array into the array. So what happened here? So we had to consider small y, okay? Small y, white train. Actually, you don't have to do the reshaping part for white. We have to do it for X test as well. So let's take X test. X test linear model is equal to X test linear model dot values dot reshape, one column. Okay, now X test LM, X test linear model dot values dot reshape. So what happened here? Let me check. So our X-train linear model data set was in this form first. Okay. First, when we split it, our data set in the ratio 70 and 30, X-train LM was a series, and we had to convert this series into 2D array. So for converting this into 2D array, so we actually extracted the values from this and we reshaped it into where we wanted one column, okay, and we got one column from that. And similarly for white train as well, X test as well, we did the same thing, X test LM. So this is X test LM data. So X train was this and X test is this, okay. So the test data is this and the train data is this. So we have converted our test and train data into a two-dimensional array. So we have performed that. And then now we have to do the training of our model. Okay. We have to train our algorithm. Okay. So we have built our model here. Let me run this code again. So yes, now we don't have any error. So we have trained our algorithm. So you can see the intercept and the coefficient. So for finding the intercept, lm dot intercept, this will give the intercept 6.74. Let's check with the previous linear regression model that we created using ordinary least square algorithm. So we got the intercept to be 6.6.74 and here also let's see the coefficient. So lm dot coefficient gives array of 0.005. So this gives the coefficient value of 0.05 for the TV independent variable that we have taken. So now let's calculate the R2 score, that is R square, okay? So print R2 score of white train. Let's do it for white train LM, comma, white train predicted. First, before that, we have to do the prediction, right? White train prediction, let's do that. White train prediction is equal to lm dot predict of x train lm. So now let's compare train lm with white train predicted. So R2 score is not defined, it is saying, right? So for that R2 score, we have to import from from sklearn.metrics import r2score. Sklearn.metrics r2score. Let me check it now. Okay. Train test LM is not defined. White train. This is white train. Okay. Okay. So we got the 64.11% as our R square. So R square is 64.1. Okay. We got the same answer. So now we will test similar thing. We will test for the testing data as well. Y test prediction is linear model dot predict of X test linear model. So print R2 score for Y train, sorry, Y test LM linear model, comma, Y test prediction. So what is the R square value we got? So R score value we get as 51.1%. Okay. Okay. So the featured columns are only TV that we considered in our example for this. What we can do is that we can consider featured columns as TV and radio, TV comma radio, and run this and go here and run this code again. Let's check what's the value we get. We have found input variables with inconsistencies, number of samples. Okay, let's run the code again over here. Let me check. Okay, let me run this code. Okay, let me run this code now. And this is not required maybe. Let me run this code. Okay, now it's fine because now array lm dot intercept is 2.95. Okay, lm dot coefficient is 0.046 for television and 0.184 for 0.184 for the radio. If you want it in the zip format, we can pass it in zip format as well. Zip of lambda of coefficient. For that we want to pass TV and radio here. Featured columns, right? Let me pass featured columns. TV comma radio. So let's include in the form of list. Okay, TV, this is the slope, and radio, this is the slope. And we can do the prediction part as well. So we get R2 score as 89.9% here, and our prediction test data R2 score as 88.69%. Okay. So what you could have done is that instead of doing here, we could have said here, could have taken feature columns over here instead. Let's take this from here. Let's run this code. Okay, so we get good results. So now let's take feature columns over here. Okay. Instead of taking here, let me take delete. Okay. Axis advertising of TV wise advertising of sales. Okay, so you can just pass over here X instead. Let me run this code from here on. Okay, from the here on, let me run this code again. Okay, X is advertising of TV. I mean, we want only the column name, right? We'll write only the column name instead. It is feature columns. So feature columns, you just change it here. What is the feature columns? Is equal to, in our case, it's TV. Okay, TV has a 0.05 slope. And R2 square is 89.64%. And adjusted R and R2 score for test data is 51.1%. So similarly, include TV and radio independent variables and check it. So now you could see that you don't have to run this line because it's in the form of a data frame, right? So you don't have to run this line. It's a 2D data frame. It's in the 2D array already. So our intercept is 2.95 and our slope for TV is 0.046. But we had to pass here feature columns as radio as well. Let me run the code again. What happened? Okay, okay, okay. We shouldn't have included this. Okay, so let me run this code again. Don't run this code, okay? Only when you are taking only one independent variable, you have to do the reshaping part. You have to convert into a 2D array. But when you're doing, when you're taking only, when you're taking a data frame, you don't have to reshape your array, okay? So sorry for running the code again. So I've taken this, so run this code again. So don't run this and run this code. Okay, we have our linear regression model. So we have our intercept and now we have our TV slope to be 0.04 and radius slope to be 0.18. Now we'll do the prediction part and we'll see the R2 score has increased from 64 to 89%. And once again, we will run this and check. So our R2 score has increased. So in the third step, what you can do, include TV, radio, and television over here. So after run this code, television, okay, what happened? Television not an indexed. Okay, now the newspaper, okay, this is newspaper. Newspaper, okay, run this, and don't run this, run this, run this, run this. So we have, okay, we have to change it to newspaper over here. Newspaper. So once again, run this from here. So our independent variables are TV, radio, and newspaper. So this is already in a 2D array. So we have our intercept 2.957. We have our slopes for each of them. And now let's do the prediction for our training data. So you can see for TV and radio, our R2 score came out to be 89.9%. Let's see how much it will come for including newspaper. it remains same. Okay, so no improvement occurred and it decreased over here. So we can say that newspapers should not be included because it is not having any impact in our sales. So this was all about the linear regression class, coding class. Hope you enjoyed the session. Uh, we will be covering the logistic regression in the next class. And okay, thank you for attending this session once again. Before concluding the session, I wanted to tell you try this mean squared error as well. So we have from sklearn, okay, from sklearn dot metrics import mean square error and then check the mean square error of y test lm comma y test predicted. Okay, so it comes out to be 2.5. And similarly, you can see as from sklearn dot metrics from sklearn metrics print dirf metrics. So you could just explore the other functions that are present over here. Like let me check. Like we have confusion matrix over here. I'm going to teach you with that confusion matrix. There are other means. We have mean absolute error, mean absolute percentage error, and also we have mean squared log mean error, mean squared error we have, and also we might have root mean squared errors somewhere over here. Check that and do the exploration part of some of the functions that are present in metrics and try to compare which independent variables give the best result for our sales and just try to remove the independent variables that doesn't have any effect on our output, that is sales. Okay, so still now whatever we have discussed, we have seen that TV and radio has high influence over the sales. So advertisement of TV and radio has high influence over the sales, over the sales, but newspaper doesn't have any influence. So this is all about the linear regression part. In the next video, I'm going to start with the logistic regression. Hope you enjoyed this session. Thank you.